The Advanced JEE has become totally online from 2018. But this has not made much difference on the pattern of questions, at least as far as the mathematics sections are concerned. The number of questions has also remained the same, viz. 18 per subject in each paper. The spectrum of possible scoresfor multiple choice questions, where out of the 4 given options, 1 or moreis are correct, has been widened to allow partial credit of 1 to 3 marks, out of a maximum of 4 marks, in those cases where fewer than the correct, but no wrong ones, are correctly identified. But there is no gradation in negative marks. They remain 2, even if one wrong answer is marked as correct regardless of how many correct answers are identified. As in the pastthere, is no score if a question is not attempted.
So let's start our discussions on JEE Paper 1 of 2018 Section 1 right after this short break, and so if you are interested or participate in such kind of discussion, please subscribe and don't forget to hit the bell button to get the video first. Paper 1 of 2018 Section 1, 1 or more answers correct. Section 1 Maximum marks. 24. This section contains 606 questions. Each question has 4 options for correct answers. 1 or more than one of these 4 options are correct options. For each question, choose the correct options to answer the question. Answer to each question will be evaluated according to the following marking scheme: full marks plus 4 if only all the correct options are chosen. Partial marks plus 3 if all the 4 options are correct but only 3 options are chosen. Partial marks plus 2 if 3 or more options are correct but only 2 options are chosen, both of which are correct options. Partial marks plus 1 if 2 or more options are correct but only 1 option is chosen and it is a correct option. 0 marks 0 if none of the options is chosen, i.e. the question is unanswered. Negative mark 2 in all other cases. Let's see question number 1, which is from the house of complex number. So as it is given, for a non-zero complex number G, let argument of z denote the principal argument with argument of z lies between -pi to +pi. Then, which of the following statements is false?
It is ironic that the very starter of paper 1 be a question which is a masterpiece of how a question should not be drafted. First of all, it is not clear what is gained by asking the candidates to identify the false options out of the forgiven ones. Logically, this is no different than identifying the true options, which is, in fact, the standard practice, and also followed for the remaining questions in this section. By breaking the convention in just one question, the paper setters apparently want to test mentalness of a candidate. But this way of doing so sounds childish.
And sir, as you know, sincere candidate may either get caught napping for a superficial reason, or he will have to spend a moment or two to see if the paper setter should some other intention in deviating from the convention.
Now coming to the mathematical aspect of the problem, because of periodicity of the trigonometric functions, the same, non-zero complex numbers can be written as r cosine of theta plus iota r sine theta for infinitely values of theta. Any such value is called an argument of z.
Any two arguments of same number differ by an integral multiple of 2pi. So any semi-open interval of length 2pi contains a unique argument of z. Fixing in such interval, we get the definition of the principal argument of z's, the unique argument lying in that interval. The paper setters have it done well to specify this interval as -pi to +pi, because another common choice is to take it as the left half closed interval 0 to 2pi. Geometrically, in the Argand diagram, if a complex number z represents a point z in the plane, then its argument is the angle which the ray os makes with the positive x-axis.
Anyway, going by the age-old convention, rather than the paper-setter's stipulation, we argument of -1 minus iota is equal to argument of square root of 2 under bracket negative of cos of negative 3 pi by 4 minus iota of sine of minus 3 pi by first, so, which on solving we get negative of minus 3 pi by 4. This is also obvious from the diagram, and renders A false.
As for b, we have f0 equals argument of -1 equals pi. Now from the diagram above, it is obvious that for t is greater than 0, argument of -1 plus iota t lies between pi by 2 to pi, while for t less than 0, argument of -1 plus iota t lies between -pi to -pi by 2. So, ft cannot be continuous at t equals 0 because limit t tends to 0 plus f of t is greater than or equal to pi by 2 while limit t tends to 0 minus f of t is less than or equal to minus pi by 2. If even only if them fails to exist, then 2 ft is discontinuous at t equals 0. B is false too. Another way to see that f is discontinuous at 0 is to get a more familiar expression for ft. If z equals x plus I, y equals r cos theta plus I sin theta right parenthesis theta theta equals sin theta upon cos theta equals y by x comma, provided x is not equals 0. This seems to give a handy formula for the argument, viz. Argument of z equals inverse of tan y by x.
But there are several difficulties in applying this. First, tan inverse always lies in minus pi by 2 to plus pi by 2, while argument of z lies in minus pi to plus pi left half open interval. The catch is that from tan theta equals y by x, it does not necessarily follow that theta equals tan inverse y by x. Theta could as well be tan 1 y by x plus or minus a graph. And we have to choose a value that lies in minus pi to plus pi open interval. Also, we have to tackle the case x equals 0. Note that if this happens, the is not equals 0. Since z is not equals 0, the easiest way out is to realize that if z equals x plus iy is not equals 0, then its principal argument of z is determined not by the single requirement in theta equals y by x, but by the joint requirements. Cos theta equals sin theta equals y.
We need the last two parts to answer B. For t greater than or equal to 0, the fourth part applies and give us argument of 1 plus iota t equals pi minus an inverse, while for t less than 0, the last part applies and give us argument of 1 plus iota t equals minus pi minus an inverse. So LHL and RHL at x equals to 0 are pi and minus pi respectively. The two limits are unequal, f is discontinuous at t equals 0. This method is slightly better because we get the exact values of both the limits. But the earlier approach was sufficient to show that in case both the limits exist, they are unequal. And that is all we need to prove discontinuity at 0.
Returning to the question, statement C is more likely to be true because of its non-commutality. It merely asserts that the expression argument of z1 by z2 argument of z1 plus argument of z2 equals 2 meters pi for some integer m, rather than for a particular integer m. Such non-specific statements are more likely to be true than specific ones, since any two arguments of the same complex number differ by an integral multiple of 2 pi. Conversely, C is equivalent to saying that argument z1 argument z2 equals argument of z1 by z2, whereby arg we now mean some argument, not necessarily the principal argument. This is best verified by a direct computation. Say z1 equals r1 cos theta 1 plus iota sin theta 1 and z2 equals r2 cos theta 2 plus I sin theta 2. Then by a direct calculation, thus we see that if theta 1, theta 2 are any arguments of z1, z2 respectively, then theta 1 minus theta 2 is one of the arguments of z1 by z2.
So, C is true. No, the wording of D is faulty. The locus of a point in a plane is a subset of that plane. It could be a line, a circle, an ellipse, etc., or only a part of it, e.g. a half ray, or only a segment, or only the upper arc, etc. It cannot lie on these curves. Points lie on or belong to subset. They are contained in the ambient set. So instead of saying that locus lies on a straight line, the correct wording would be that it is contained in a straight line. Or, the word locus could have been dropped altogether.
The crucial task is to identify the nature of the locus from this.we did this only in two special cases, viz. z1 equals 1, z2 equals 0, z3 all real and z1 equals 1, z2 equals 0, z3 equals I. The fact that in the second case the locus is a part of a circle is sufficient to dismiss D. But that leaves open the question as to whether the locus can form a part of some other curve such as an ellipse with some other choices of z1, z2, z3. It turns out that this does not happen. The complete answer is given by this theorem. Theorem states let z1, z2, z3 be any three distinct complex numbers, and then S is either a straight line or a circle, with one point removed. A geometric proof of this theorem, of which we have verified only two special cases, will be indicated below. The true significance of the expression, which looks highly clumsy to say the least, is well beyond the scope of the G syllabus. It is called the cross ratio of the four numbers z, z1, z2, z3, in that order, and denoted compactly z, z1, z2, z3. It plays an important role in studying what are called fractional linear transformations.
The G syllabus on complex algebra does not include fractional linear transformations and cross ratios. Although technically, D can be answered without knowing either of these concepts or the theorem above, as we have done, the question properly belongs to an advanced syllabus. It will give an unfair advantage to those candidates who happen to know the theorem above. Others will get confused or might mark D as true from the special case when Z1, Z2, Z3 are all real.